Um, just a minute, there are some people in the waiting room. Okay, welcome everyone to the 62nd meeting of New Directions in Group Theory and Triangulated Categories. Today our speaker is Wilberd van der Kallen from Utrecht University, and he'll be speaking to us about a Friedlander-Suslin theorem over a noetherian base.
Thank you. For those of you who want to get a copy of the slides, you can go to my web page. If I click on it here, I get there, but I don't know. That may not work for you. Hey. Oh, yeah, so the interface changed because I'm not using full screen now. So here's the plan of the talk. There are pages and they have titles. The first one, I will recall the theorems of Evans and Friedlander-Suslin. Then I'll talk a little bit about my conjecture. And then about work with Srinivas towards proving that conjecture. And then a variation with noetherian base ring. Then I'll talk a little bit about work with Franjoux, about invariant theory over a noetherian base ring. Then David Benson will come in. He gave us some hints on cohomology. And the conclusion of all that is that bounded torsion is somehow relevant. And then I'll remind you that originally our main topic is finite group schemes, and so we will have to induce up from finite group schemes to get back to make contact with this story. And then I'll just look at the simple case of a finite group, and then I'll tell you what I found in the literature on Hopf algebras, and that will then finish the argument. Okay, right. So the theorems of Evans and of Friedlander-Suslin. We start with the theorem of Evans. That was in Transactions of the American Math Society, 1961, so that's quite a while ago. He took a finite group. His base ring was a commutative noetherian ring. He had the group act on the finitely generated commutative K algebra A. This will always be the setting today. The group or the group scheme will always be acting on A, and A will be a finitely generated commutative K algebra. Then the cohomological finite generation theorem, as I call it, of Leonard Evans, says that the cohomology, this A is an algebra, so this cohomology will also be an algebra, and his theorem was that that's a finitely generated algebra. Now, people working in finite representation theory of algebraic groups thought that was very interesting, and they wanted to apply that, but with a slight variation. Let's take the base ring to be a field, and instead of a finite group, they wanted to do it for a finite group scheme over K, which sounds practically the same, and let's have it act again, and you want to conclude that someone is making noises. Should I have heard it? Okay.
No, it's all right. I have muted them.
Okay, so now there is a long time between the theorem of Evans and of Friedlander-Suslin, and the reason is not that there was no interest. It was just that to make this little step from a finite group to a finite group scheme, it was, as as Friedlander-Suslin expressed it, it was surprisingly elusive. They had to invent whole new tools, which I will not talk about today. But so their theorem is the same conclusion, but I'd better say a little bit what is a finite group scheme over a field. Well, that means it's an affine group scheme. So it's as a scheme, it's a spectrum over some ring. I call that ring the coordinate ring. Of course, it's more than a spectrum, it's a group scheme, so the coordinate ring should be a Hopf algebra. But in particular, it's a vector space over K, and a finite group scheme means that that vector space is finite dimensional. Okay, so that's the meaning of their theorem. And now I want to, so the claim today is that you may replace the field with a commutative noetherian ring, thus unifying the theorem of Friedlander and Suslin and the theorem of Evans. Because if you have a finite group, then the group ring is a Hopf algebra whose dual is the coordinate ring of a finite group scheme, and these cohomology algebras have the same meaning. So now don't think that you now have a better proof of the theorem of Evans. The new proof, although it's independent of the proof of Evans, is just a disaster compared with the original proof. Okay. Right. But so when I say that you may replace the field with a noetherian commutative ring, then I'm assuming that you know the convention, what a finite group means in that case. In that case, it means that the coordinate ring is a finitely generated projective module over K. And so if you don't know that convention, then because the base ring is a commutative noetherian ring, you may express it differently. You may say that as a scheme, it should be finite and flat over K. So flatness really belongs there. It's either by convention, but you really need it. All our group schemes today will be affine group schemes flat over the base for a very important reason. Namely, we want the G modules, no, the functor from G modules to G modules, which sends a G module to its subspace of invariance, the subspace of the fixed points. We want that to be left exact, and we want to take its derived functors, and that's what the cohomology is about. So we definitely need flatness.
Wilberd, there is a question in the chat. Can you have a look at it?
No, I don't see the chat. Where's the chat?
Okay, let me read it out. So this is a question from Julia Pepsova. So she says, I think Friedlander-Suslin only look at finite modules over G, and hence finite dimensional algebras A as coefficients. Is it an easy generalization to finitely generated algebras A?
Well, I complained to Friedlander that they had not looked back at the original paper when they wrote their paper. But basically, they prove it. And I have a line in my preprints explaining how to get from their paper to this statement. It's really it's really very easy, but they didn't. They just forgot to look at the original source. That's what happened. So, yeah. But, oh well. Their proof was nice enough, and it also covers this. Okay, so what about my own conjecture? Well, now a K is a field, and I'm looking at the reductive group scheme of a K. Well, and I have it act on the commutative K algebra as always, and my conjecture was that the conclusion is still the same. You still have cohomological finite generation.
Wilberd, I'm sorry, there is another question in the chat. I'm really sorry. Well, I mean, the question is from Anton Fonarev, and he asks, is there an easy counterexample for the statement when one drops the flatness condition?
Counterexample to which statement? I don't have the cohomology. I define the cohomology as the derived functors of this left exact functor. But if I don't have a left exact functor, what do? Okay, I'm cheating. You could define cohomology with the Hochschild complex, but I think that's just artificial. I mean, I think this is about homological algebra. And when you don't have the homological algebra, I refuse to think about it. So my answer is, I refuse to think about it.
Thank you.
Yeah, so what was the reason for my conjecture? Well, the reason was that I thought it wasn't true, and I kept looking for counterexamples, and I was running into more and more evidence that it was actually true. And at some point, you just have to listen to the mathematics. So it wasn't like some people think that, oh, I want to imitate this nice statement. No, that wasn't it. I just didn't think it was true. But okay. But so in the previous century, I believed it was false. Okay. And then at some point I gave up. And that's the conjecture. Then, yeah, so it was proven by Antoine Touzé in 2000. Well, you can read it in Duke in 2010. Antoine was a student of Franjou, and that's how I got to work with Franjou. Actually, I got to work with Franjou on a day that Antoine was busy. Yeah, so the proof of my conjecture had several parts. The work of Touzé provided the last and most difficult piece of the puzzle. And one of the early ingredients was I done with Srinivas using a method that he calls resolution of the diagonal. That's a bit short. So it uses something about functorial resolutions of the sheaf of the diagonal in a product of two Grassmannians. The two Grassmannians are, of course, copies of the same Grassmannian, otherwise you don't have a diagonal. And so you think about that as a correspondence, as a graph of the identity map, and then you start playing strange games with push forwards and whatnot. So what's the result that we got that way? Well, let's say, no, we actually got the result for GLN. It's not, let's say GLN, it was about GLN over the field. So recall that a representation is said to have a good filtration if it has a filtration whose successive quotients are what we call co-standard modules, and those are modules which are induced up from a one-dimensional representation of a Borel subgroup, say in this case from the upper triangular subgroup. That's all mouthful, but those are our favorite representations. They have no higher cohomology, and they are the building blocks for the derived category, blah, blah, blah. Yeah. Now, there is a cohomological criterion of Donkin for when a module has good filtration. I have rephrased this a little bit, and I say, well, it has a good filtration if and only if the higher cohomology of SLN with values in the representation V tensor over K with this nice algebra, if that vanishes. That's my own formulation. And the reason I like it is that this algebra here of functions on SLN invariant on the right translation by U, that's an example of a finitely generated algebra with good filtration. So, well, finitely generated algebras are the topic today, right? So, yeah, so now what does our theorem say? That if this A happens to have good filtration, and you have a finitely generated equivariant A module, then that module must have a finite resolution by A modules with good filtration. And so in particular, its cohomology will vanish in large degree, because you resolve by things that have no higher cohomology. And no, that's useful in attacking my conjecture, I can assure you. Right. Now, so that was over the field. But now suppose we take a commutative noetherian ring. Then our joint paper didn't work. But at some point I discovered that if you just change the meaning of the term negligible, which occurs a lot in that paper, then the proof could easily be adapted to the new situation where the basis is a commutative noetherian ring. And so what I do, I took the text file, I removed my co-author, I changed the definition of negligible, and I started going through it line by line to see what needed to be changed. It would have been a terrible pain to explain to the reader what to change, so it was much better to do it myself. And then at the end, I added a section with conclusions, what the new situation was now. So, but the arXiv, they inserted an arXiv admin note warning that there was a significant overlap of the text files. Yeah, it wasn't entirely fair because the text may have been the same, but the meaning was not. I mean, there were 38 occurrences of negligible, according to my tool, and each time there, you couldn't just, no, well, you just had to reason again. Anyway, so the French didn't mind. They thought this was very suitable for their volume celebrating SJ3, because it turns out that I get conclusions for groups schemes that are reductive over the base in the sense of SJ3. So that was very suitable for that. And also the title now doesn't say good filtration, but it says good Grossans filtration in a family. The family just refers to the base. And the reason is that this cohomological criterion I told you about in this context no longer gives you the things that are known as having good filtration. So I needed a new name because I'm still using the same cohomological criterion. Okay, so that's the significant overlap paper. Then let me go to my work with Franju. So we were asking ourselves, okay, so when Toussaint is finished, what would be a good thing to look at? And so we thought, well, maybe not just fields, but other base rings. But if you're trying to think about the full cohomology ring, you'd better first understand the zeroth one. So that's about taking invariance. So the first thing we needed to understand was is the ring of invariance still finally generated? So does the first fundamental theorem of invariant theory still hold in this kind of generality? So what we did, we were just amusing ourselves. So we were telling each other, okay, what do you know about how proofs go over a field? And then let's go and check what needs to be changed. Okay, so we did that. And we concluded, well, nothing has to be changed. It just works. But that's, of course, only true for the proof that we told each other. Yeah. So then next day, we started asking around what's known about this, and we asking for references, and then and then we were shocked because the literature made the issue look much more difficult, and it didn't even get to the general statement. And so we soon discovered what was wrong, what had gone wrong. What had gone wrong is known as geometric reductivity. Habush had used geometric reductivity as a stepping stone towards proving finite generation. Well, I mean, that other step was taken by Nagata, but it's a misunderstanding that you shouldn't be using a geometric reductivity as the stepping stone to finite generation in this setting. The problem is that a geometric reductivity is phrased in terms of functions on representations, but G modules are no schemes. So having functions, that's not a natural thing to do. It only works if the G module happens to be a finitely generated projective module over the base. But those are very rare in the abelian category of representations. And our A is just sitting in that much larger category. And if you're using these very special representations, you're not seeing the full category very well. Also, we know from Nagata's proof that we should be looking at all equivariant quotient algebras of A. So in particular, you shouldn't expect things to be flat over the base. So it's entirely the wrong stepping stone. And the right stepping stone is what we call power reductivity. Well, I gave a definition here. The notion is not very original, because it turns out that if you just look how Mumford formulates his conjecture in the first edition of the GRT book, then you say, power reductivity. And so what happened was that people did not take the formulation of Mumford sufficiently seriously they have thrown in a dual, but these things, well, over a field, that's an innocent thing to do, but over a noetherian ring, that's not such a good idea. So, but we were just ridiculously lucky that our proof just happened to be the one that we told each other was just the one that generalizes. To mention a detail, we took Springer's exposition of Nagata's proof. Springer's exposition generalizes. Nagata's proof, there is a difficulty. Okay. Anyway, so that was that's that. So next, of course, we then thought, well, okay, let's look at higher degrees. And then we got some help from David Benson. He said, well, you should go and read my paper with Haberger in the 80s. It contains some tricks, and you may find them useful. Well, he was right. So what did we learn from that? Well, we learned that suppose you have a positive integer that annihilates the positive degree cohomology of the algebra we care about. Yeah. And suppose you have a prime number and you take you take a positive degree, you take a class, but now a class for A mod P, for the algebra A mod P. Then the claim is just by playing with long exact sequences of cohomology attached with short exact sequences and a little functoriality of that, changing some diagrams and well, anyway, using their tricks, you see that some power of that class actually lifts. And so that means that you get a close connection between the algebra we try to understand and the algebra here, where now, well, A mod P is, of course, an algebra over K mod P, and K mod P contains a field of P elements. And so that's much closer to the work of Touzeau, and so you can make contact with the work of Touzeau that way. Now there's a little cheat here. I'm writing the cohomology of G with values in A mod P, but I'm not telling you how to read this, what the base ring is. Is the base ring K, or is it K mod P? The notation doesn't say.
Doesn't matter.
The joke is, it doesn't matter. The Hochschild complex for the two contexts, the two Hochschild complexes are isomorphic. This is an observation that I could not find in the literature. But just saying that it's so, I mean, everybody can check it. Good. Where am I? Right. So that was, okay, so now we have to take these things together. And in my paper with the new meaning of negligible, which appeared in 2015, we see the following theorem. Suppose we have this noetherian ring K, we're looking at GLN over it, we have this algebra on which it acts, which is of course finitely generative commutative algebra, and the action is of course be the action of the scheme. And then now suppose that there is a positive integer n that annihilates all of the cohomology in positive degree. Then actually the cohomology algebra is finally generated. So this combines Touset, David Benson, and well, all the above. And if there is such an n, then we say that this has bounded torsion. I mean, it's a reasonable terminology, right? So that's, well, that is what was understood in 2015. And I do not remember why I didn't try to prove the theorem that I'm talking about today. Maybe I was just hoping that there would be much more general progress or whatever. Anyway, I don't know. So, but let's return to our to the situation we in the main result. So K noetherian, a G finite flat group scheme, and we want to prove the Friedlander-Suslin theorem. Now, what do you do? This is a standard trick. You embed our finite group scheme into some GLN, so some faithful representation. Then one knows that the quotient variety, so the functor of right cosets or whatever you call it, that's an affine variety. That's something that belongs in invariant theory. And then the cohomology of G with coefficients in A that you're trying to understand can be rewritten in terms of cohomology of GLN of the thing that you get by inducing up from your finite group scheme to GLN. Now, this induced up thing is itself a finitely generated K algebra because it's well, you get it by taking G invariants, and so finite generation is preserved. So what's the situation? You're trying to understand the left-hand side, well, not just in positive degrees, but you try to understand the left-hand side, but we know something about the right-hand side. Namely, we know that if this has bounded torsion, then you would be okay. Well, but to show that the right-hand side has bounded torsion, it's the same as showing that the left-hand side has bounded torsion. But on the left-hand side, that should, of course, be easier because this is a finite group scheme. And that's pretty close to a finite group. And okay. And yeah, so why didn't I do that years ago? I don't know. But why did I do it now? I do know. Srinivas visited my country and he was asking questions. And I was dissatisfied with my answers. So that's how come I looked at this topic again. Okay, now there are two cases. That is the case that our ground ring contains some finite ring. In that case, obviously the torsion is bounded because I mean, if our base ring contains Z mod n, then everything is annihilated by n, and there is your torsion bound. So we may further assume that that our ground ring contains the integers. Yeah. Okay. Now, let's, by way of exercise, go back to the case of a finite group, because for a finite group, everybody knows that the cohomology is killed by the order of the group. The cohomology of positive degree, of course, not the H0, that's the invariance. I mean, there's no reason that would be killed by the order of the group. But so what about a constant group scheme? Oh, that's a very fancy way of saying, what about a finite group? Yeah, there are several ways to prove that in the literature, but you can really, there is really very down-to-earth way of going about it. You use this, you use the element of the group ring, which is the sum of the elements of the group. Yeah, I make here some, well, okay, let's skip that. And, you know, suppose you have a surjective map of G modules for our finite group, and we have an invariant in the image module. Then, of course, it's the image of something. And then everybody knows that if you average it, that will be an invariant. But of course, it will not hit the original element. It will hit n times that element, where n is the order of the group. Okay, so what you see is that n annihilates the co-kernel of the map between the invariant modules. This is the invariance in V, that's the invariance in W. The co-kernel is annihilated by n. And well, then you just argue by dimension shift that this remains true if you if in higher cohomology. Oh yeah, okay. So in higher cohomology, okay. So first, okay. So the way you do this is you take yeah, well, you argue by dimension shift, and how do you do the dimension shift? Remind me, right? Yeah, okay. So you need to show that yeah. So n annihilates the co-kernel here, and that co-kernel sits inside an H1. And if you if you now have your favorite module, then you put it inside an injective module, then you get a short exact sequence, then you apply what you just learned, and then you see that the first cohomology is annihilated by n, and you repeat that. Okay, so this proof we need to generalize to our finite group schemes. Well, what do you need for that? You need to know something about Hopf algebras. Well, I'm not an expert on Hopf algebras, but I found a paper by Bodo Paredes who does exactly what I need. And I knew his name because he was the reviewer of my first paper. And in the same year as that, he wrote this very useful paper. And yeah, so anyway, so he so what does he show in his Hopf algebra paper? he shows that what he calls left integrals right. I should explain what kg is. I have a finite group scheme, and that one has a Hopf algebra, and then its dual is again a Hopf algebra, and I'll write kg. It looks a little bit like a group ring, which is indeed I'm trying to suggest it behaves like a group ring. kg is the dual, and I'll try not to pronounce the coordinate ring as kg, because kg is now the other one. So this one I will just, what do I call it? I call it coordinate ring. Yes, that's what I call it. Anyway, so what he shows that in general, the so-called left integrals in this kg span a summand that's a projective K module of rank 1, where a left integral is an element of this dual, which, well, because it's a dual, it defines a K-linear map, but this coordinate ring also has an action by left translations, and what you, in the special case that this K-linear map is actually a G-module map, you call it the left integral. Okay. Another way to say it is that psi is a left integral if for any psi in that kg, you have the following rule: left multiplication by psi is the same as multiplication by the value of psi at 1. So this is anyway. So that's a left integral, but the key statement is that these things form a projective summand of rank 1. And yeah, so the thing to compare it with is when you have a compact Lie group, then this is like the averaging operators given. So averaging over the Lie group when you that's the way of getting the invariance in that context. Well, okay, but so now what we want is we want to use such a left integral, but we don't like projective K modules so much. We much prefer to have 3 modules, but But fortunately, our yeah, so let's go back one page. We were trying to, we were hoping to show that something has bounded torsion. Yeah. Now, for that problem, you may as well go local on the spectrum of K, because suppose, for instance, you have an open set where everything is annihilated by 3, and you have an open set where everything is annihilated by 5, then on the union, everything is annihilated by 3 times 5 is 15. So if you don't care what exactly, how big the torsion is, but you only care that there is one number that kills all, then you may as well go local. But if you can go local, then you don't have to worry about projective models anymore. You may take it free. So let's do that. And we have now the situation that this rank 1 module of arXiv is free. And so say we have a generator, this is psi. Now what we would like is, we would like to have an integer, as on the previous page, that integer n here. But of course, so the thing we try to show is that the psi of 1 is an integer, but of course that will not be true in general. But we may still choose which we may choose which element to use. I mean, we're not stuck with a very specific psi, but as soon as our module is free, we can at least choose the generator psi and then hope that some multiple of it will take a value which is the integer that we need in order to argue, as on the previous slide. So okay, so we must show that some multiple of psi sends the element 1 of the group ring, group ring to the coordinate ring, to a positive integer n. But for that, you may as well invert all positive integers, because if after inverting positive integers, you can hit a positive integer, then before inverting, you also must be able to do that. Just keep multiplying. You get rid of the denominators. Aha. But so now we're over the rationals. And now our problem becomes, wait a minute, what are we trying to do? Well, we are trying to get that so what is it we used here? Well, yeah, so how should I say this? So Yeah. Well, I'm getting confused, but I can assure you it's obvious. And what we need is we need that our psi that some multiple psi is a sends the unit element to a positive integer, but in fact, once you're in characteristic 0, what you actually expect is to have a unit. I mean, you can now, in order to, if you try to hit a positive integer, but you're working over Q, then you're really trying to hit the element 1. Up to multiple. Okay, so now so the thing I really okay, so that somehow I knew how to say this, and it's yeah. Okay, so what we, in order to see that that after this base change to characteristic 0, you're okay, you have to convince yourself that you're actually staring at something that takes invertible values. So you may as well go modulo a maximal ideal of your ground ring, and you may also go to an algebraic closure, and by then what you're looking at is a finite group scheme over an algebraically closed field of a, well, the short story is that what you're looking at then is just a finite group. But we've already done that. So that's the proof. And I didn't tell the last part very well, but I can assure you it's obvious. Okay. Right. And then my final slide is a problem. Namely, I don't know what happens over the integers, and I have no guess. Why did I? I'm totally lost. Sorry. I'll say thank you.
Thank you, Wilberd. Can we all unmute ourselves and give Wilberd a round of applause? Okay. Do you have any questions? If you have any questions, you can ask them now.
I have a question about the left integral PG. Sorry, can you hear me?
I didn't hear the.
Oh, sorry. I mean the slides before, one page before. Yeah, about the left integral PG. I mean, so the coordinate ring P bracket G is a finite projective module over K, right? I mean the key coordinate ring key bracket G. Just the thing before equivalent. Yeah. This one is a finite projective module, and the left integral Kg is a rank 1 submodule of the dual of the coordinate ring. Am I correct?
I'm afraid as I don't hear you well.
I mean, I want to know what is the left integral Kg. But anyone else can hear?
Left integral?
Yeah. Yes.
Left integral?
Yes.
Is well, there are two definitions. So when you have an element of this Kg, it defines a it defines a linear map. But now, when you want this map to be G equivariant, then you call it a left integral.
Okay, so a left integral is an element in the home space from Kg to K bracket G to K, and that is G equivalent.
Yeah. But because this Kg consists of linear maps from Kg to K, by definition. So this Kg is by definition the dual Hopf algebra to that Hopf algebra.
And I think your next sentence is the last is for K in K bracket G. Yeah. Yes.
The K of G is dual to this to the coordinate ring.
Yes.
And so the coordinate ring contains an element which is 1. And so you can apply an element of KG to it.
Okay.
And yeah, and this is just the multiplication in that thing.
Okay.
But yeah, but so the point is that you have you want to be averaging, and so you want something that is itself yeah. So this anyway, so but he calls them left integrals, I think.
Okay, thank you.
Yeah, Peter.
Okay. Yeah, Wilberd, thank you. This is, I just love the way you make all this hardcore homological algebra understandable. there was just one place where something I really didn't understand. There, you localized on this K at the end there. You went to the some prime ideal of K. And then you looked at the integer n, which would annihilate the cohomology at each local point, right?
But
So you
no. At the end, I'm over Q.
no. I mean, just a little bit before that, there was a point where you localized on K. You went to local on spec K, and then you changed from a projective module to a free module. That was like in then your next to last slide.
Oh, maybe
It's page 12,
Yeah.
here.
last paragraph.
Yeah.
Where did I go local?
So he says, our bounded torsion problem is local on spec K. Just at the last paragraph there. The bounded torsion is local on spec K. And so you said it's enough to look at one prime. Is that right?
No.
I mean,
No. On the risky open sets.
aha. Okay, I see. So you need a, oh, I
Is
see.
it the-
You're
is it the
localizing at
spec K
you're localizing at a divisor. Is that it? That is your
restrict to an open set.
yes. Okay, I see. I see.
And
so
I say
Uh-huh.
that if I can do it on a finite cover, then that's enough, because then
Okay,
you just
okay.
multiply them all.
Okay. Okay. I see. And
Yeah.
so if you invert one divisor, then a projective module becomes free.
Yeah.
Wow. Okay. Thank you.
Yeah. No, it's it. Yes, it's I found the projective module too difficult, so I thought, let's get rid of it. Let's make it free. I mean, maybe you can tell it with projective modules, but I thought, come on, because I don't care at all what the bound is, as long as I have a uniform a integer that kills. I don't care which one.
There's a question in the chat by Julia. Oh, sorry, Henning. Let me take Julia's question first, because it's like time-wise, I think this is a better idea. So Julia says, could you say a bit more, Julia Pevsova says, could you say a bit more about the proof of the main theorem, bounded torsion implying finite generation? You didn't tell us what negligible meant, but maybe it's possible to indicate how good Grossans filtration and finite resolutions by modules with good filtrations come into play.
The Grossans filtrations. Did I? What?
Can you see the chat? There should be a button down below.
All
It says
right.
chat.
Yeah.
Just click on it. You should. I think you will see these messages there.
Wait a minute. Which one? Julia?
Yeah.
Bounded torsion implies finite generation. Wait.
Slide 9.
Is it slide 9? Is this the one?
No, this is 10, I think.
Wait. How do I get it up?
Yeah. No, this is 8. The one after this.
After.
Yeah, this one.
Wait a minute. Huh? I'm totally lost. Wait a minute. I seem to be on an wait a minute. I'm in a different slide. Or what? No?
No,
I'm totally lost.
You're in slide 1 now. Just keep going forward and then go to slide 9. 3, 4, 5, 6, 7, 8, 9. Yeah, now. No, go back. Go. You're in 11 now. You have to go back 2 more. 10, 9. Yeah, now it's fine.
It seems to me that what you were saying back then in the talk is that 2Z has this rather strong theorem that goes back, uses the methods of Friedlander and Suslin. And then this mod P trick lets you connect to the work of 2Z. And so in some sense, the work of 2Z is the hard work. And with this positive integer that annihilates thing, you can reduce to that. So that's probably some sort of answer maybe to the question. I mean, it's sort of in the previous slide, actually, dare I say, said, if you go back one slide, you were talking about, what knowing that something annihilates lets you do. It lets you reduce to, the last line. P mod, the P mod PK, right, contains a field. So you didn't say details, but that's what I took out of this.
Yeah, but
that you want to get to.
I think I'm sweeping an awful lot under the rug here, and I understood this in 2015. And but but no. This is no, this is I don't know anymore. But this 2015 paper, that was when I was still young.
Yeah, Henning, you had a question?
Yeah, first of all, much thanks for this talk, Wilberd. I want to get back to this conjecture you made, and which eventually this finite generation, if you have a reductive group scheme acting on a finitely generated algebra, and Antoine eventually proved it. Why did you not believe in that conjecture at the first place? I mean, were there some sort of funny examples, group schemes, say not defined over field, or the integers which you had in mind?
No. But no, No, I thought I thought it was much too strong. I mean, I couldn't believe that that it would be so simple. And you know, I thought I tried to do what Friedlander and Suslin eventually succeeded in doing, but I noticed that well, you could induce up to GLN and then start worrying there. But then I thought, well, but then you should only try to prove things that came from down there. And I just didn't. I just thought it was ridiculous to expect. And I tried to, but then I started to encounter things that were unexpected, and the explanation that seemed to be the most reasonable was that this is actually true. But I started out with not believing it, but thinking that that you could use things just like I'm doing today by inducing up and studying it upstairs and hoping that for GLN you understand more and then cover what then get some grip on the original problem. But yeah, I just couldn't believe that. I mean, it sounds the same as the other statements, but there was no reason to believe it.
Okay. No, I thought maybe you had some examples, but this is
no. I had
you had lots of
I didn't get examples.
Yeah.
Because no, of course, in the examples, there were two kinds of examples where I couldn't decide, and examples where it was true. But I didn't consider that as evidence. But because the but so it was but I started to prove things that were just strange if it wasn't true in general. And then, okay, I changed my mind and I started believing it.
Yeah, thank you very much.
Thank you, Henning. Any other questions for Wilberd? You see a raised hand? No. Okay, if there are no more questions, let me thank you all for coming here, and let's thank Wilberd one more time.
Thank you.
Okay, I'll stop recording now.